So after we drop the data, we're going to impute the data using a random forest method from the misRanger package. So there are many methods to replacing NAs. We could replace with the mean, but that could be considered oversimplified, right? For, say, SDG score one of the no poverty measurements, if we just had a mean of maybe the percentage of folks living underneath the poverty line, we took that mean for all the countries, and any country that didn't have that information, we replaced the NA value with the mean from the rest of the countries. That would be that technique. It is oversimplified and it doesn't really reflect what we want it to. So we're going to go a little bit in a more complex way. We could use cluster imputation. So can we guess the score based on countries that are similar to it in a lot of the other scores? I think that's a better way than just replacing the mean. But the way that I think makes the most sense for our case is imputing with decision trees or random forest. So the main takeaway here is that there are many ways to handle missing data with our data set, but it seems that training a model to predict the missing values with decision trees based on the rest of the data is the most rigorous option. So this, again, could be a course in itself, but I just wanted you to take away that there are many ways to handle missing data. We need to fill the NAs with something just so we can run our clustering algorithm and our random forest algorithm. We actually use a random forest to try to predict those missing values based on all of the other data in our data frame. So we use the misRanger function here, and after that, we guess or impute all of that data. So we have a data frame with no NA values, and we'll take a look at that a little bit deeper when we jump into RStudio. So now let's look at clustering. So are there groups of countries based on SDR 2023 scores? How many groups are there? Which countries fall into which group? And we have a link to an excellent guide on k-means clustering if you really want to get into the methods of how we cluster and what the math looks like. But we're going to follow a similar method to them and use k-means clustering. So before we do that, let's go into some of the specifics on the setup before we can use the k-means function. So we remove the row names and make each country the row name. It's kind of just a specific part of what we need to feed into k-means. And then after we do that, we can use this fviz nbclust function to look at how many clusters are in our data, right? So we're presenting this function with a data frame, and we're asking the question, how many clusters do you think there are in this data frame? How many groups of countries? And wherever that dashed line is, that is the number of clusters that this function believes is in the data frame. So it starts us off with 2. This is something that we can change and we can play with, and we will in the code in the RStudio version of this video. But for now, we're going to stick with 2, that there are 2 clusters in our data, so 2 groups of countries based on SDR data. So when we use k-means, and this is our clustering function, we'll feed it our imputed data frames, or a data frame that doesn't have any NA values, because we use the random forest method to predict them. And then we'll use centers equals 2, and that's simply just the number of clusters in our data frame that we got from this fviz nbclust function that laid out with the dashed line how many clusters we should have. The fviz cluster function, and we'll feed it the output of our k-means algorithm that we named k2 and our imputed data frame. And we'll look just with this plot that seems very cluttered, I know, but this is how the countries are separated into the 2 clusters. Countries that are closer together here are more similar, and the ones further away are more different, right? So within this plot, we can see that there's just this break that divides our 2 clusters. And with the code below, we'll examine, okay, which countries are in cluster 1 and which countries are in cluster 2, just with a simple data frame. So this concludes the clustering part. We'll talk about it a little more in the RStudio segment of the video about which countries fall into which cluster and how to even tweak the number of clusters to get some different pictures and maybe some more specific information. But now we'll continue on with our random forest regression. So I did want to take a step back and just speak on, okay, what are random forests and what is the whole point of this exercise? Titanic data set. So each row is a passenger, and each column has information about that passenger. So things like a passenger ID, whether they survived or not. So 0 being they did not survive, 1 being they did. The class, their name, their sex, their age, their ticket number, the fare they paid for their ticket, their cabin, etc. Right? So all information about these passengers. And the goal with applying machine learning to this is seeing, can we predict that survived column? So whether a passenger survived or not, based on all of the other data in the data frame, all of the other data about them. So their passenger ID, their sex, their fare, can we use that to make a prediction to see whether they survived or not? And we already know if they survived or not, right? It's in the data frame, but there's lots of reasons for making this prediction, and we'll see why. So in making the prediction, we could use a lot of different methods. One of them is a random forest method, and it's kind of a bunch of decision trees that look like this. So is the gender male? Is it an adult in third class? And as you get through each one of these decisions, you end up at the end of the tree with a survival rate. So this person maybe was 25% likely to survive, or possibly even 100% likely to survive, right? Based on how they go through that decision tree, based on the information about them. So a random forest is a large amount of these decision trees, so hundreds of these decision trees, hence the term forest. So lots of trees in this random forest, making decisions or making predictions, survival rate predictions, based on all of the information about a passenger. And once we do that, once we ask the random forest to make a prediction based on all the data, we can ask it, what were the most important columns or variables in the data set in making the prediction? So was gender more important in making the prediction than class? And that's what we see here with this feature important plot. So what variables in our data set were the most important in making the prediction on whether a passenger survived or not? And this tells us that gender was. And even if you look at the raw data, there's lots of information about 70% of the female passengers surviving and maybe only 18% of the male passengers surviving. So gender plays a big role. Class plays a big role. Age, lots of young were saved first. Elderly folks, right, had challenges on being saved, so they put the young first. The fare was very involved or very important in making the prediction of survival. So we get to see classes here and which were the most important. And lastly, with the Titanic, we get to see by age and by fare, what did the average prediction of survival look like? So we can see here on this left diagram, when we start with ages that are very young, right, like between 0 and 10 maybe, you have this 55% average chance of survival. But as you get older, that quickly spikes down, right, to around 30%, and even dipping below the older you get, right? So age, like the very young had the highest probability or highest prediction of surviving. And fare, it looks like as you increase that fare, right, it's also linked to an increase in the average prediction of survival. And what if we looked at these two together? So if we looked at age and fare together, and these colors, right, these segments are based on a 0 to 100% prediction of survival. We see the sliver that's at a very low age here is all yellow, so very high prediction of survival. But then we get into these lower color segments, and we start to see, like, for age, as age goes beyond 40 and fares stay very low, we have the lowest probability of survival, like between 20 and 30%. But if you're older and your fare is a little higher, around 100, you have between 30 and 40%. And if your fare is above 200, it looks like you have between 40 and 50% chance of survival. So these are the ways that age and fare kind of interact with each other in the prediction. So age definitely has the most important predictor, right? The most important, the highest prediction being at very young ages. But we can see how age and fare kind of interact with each other here in making predictions. So it gets really neat. You see these kinds of examples everywhere, and it's going to tie really closely into the predictions that we're going to make. with our machine learning model, with our random forest model. So let's dive into it. So we'll use the random forest function that we'll talk about a little more when we open up RStudio. And we're going to ask it to predict maternal mortality. So the normalized score for maternal mortality under SDG 3. So can we predict that for each country based on all of the other data in the data frame? And we set importance equal to true so we can generate and see which are the most important features in making that prediction. So our model is relatively accurate. We see here with a mean error rate of around 10%. So between 0 and 100, right, were the possibilities for that normalized score. And our model had about a 10% error rate, so not the best, but not doing poorly by any means. And the value of 80.83 for that variance explained here. It says 80.83 of the variance in the target variable is explained by the predictor variables included in the model. So there is some variance that isn't explained with the data that is in our data frame. And we expect to see that, right? We're not going to account for everything just in the data that we have. So as we continue down and we made these predictions and our model is somewhat accurate with an error rate of around 10%, we can ask it, what are the most important features in predicting normalized maternal mortality scores? And here we get at the top of our graph, these are the top 10 predictors. Sanitation, under 5 mortality, electricity access. So things that do make sense when we think about them, right? They might not be directly related, but they do serve as strong predictors of this maternal mortality score. And as we go down a little bit, we can see, so y hat is the model's prediction of a maternal mortality score. And remember, these are normalized scores. So the higher the score for maternal mortality, the better that country does in regards to maternal mortality. And you can see here on the x-axis, we have normalized score for sanitation. So for our top variable. And once that score hits around 40, the predicted score for maternal mortality starts to jump, right? So we go from around 76 to 82. And then eventually, as it gets higher, we get to about like an 85 predicted score. So the range again is only from 76 to 85, but it is relatively important, right, in the distribution of the scores for maternal mortality. That is a big jump, like 10 points, right? So we can see, right, like what are the thresholds when we get a certain score for this sanitation variable, when did it start to increase the prediction of the maternal mortality score for a country? And that's what we see here. And there's a little bit more language here about how to interpret that model. And then similar to how we saw age and fair and how they work together, can we see the score for under 5 mortality and the score for sanitation and how they work together with that same legend being a prediction of the maternal mortality score? So we see one little slice of yellow here, right? Saying that when the normalized score for sanitation is very high, close to 100, and the normalized score for under 5 mortality is very high for close to 100, our random forest model is predicting a very high score, close to 100 for maternal mortality. But as those scores lower, we see this gets darker purple, right? And those predicted scores start to drop, right? So we have in this bottom where there's low under 5 mortality scores and sanitation scores, the prediction for maternal mortality is around under 70% or under 70 for their score. And we see thresholds again, right? And these don't have as different of a relationship as age and fair did, but there is some interaction here with how sanitation works and how under 5 mortality works in the model and how those predictions get made. So it's a little bit of an underlying feature. So now that we saw how one variable influences the model prediction, how about two variables? So the same way that we looked at age and fare for the Titanic, can we look at our top two variables of sanitation on the x-axis and under 5 mortality score on the y-axis and see how those variables interact in making the prediction for our maternal mortality score? So we see here this very bright yellow is the highest prediction of maternal mortality score. And that's when the normalized score for sanitation, the normalized score for under 5 mortality are very high, right? Very close to 100. And that intuitively makes sense. When those scores are very high, our model is predicting that the maternal mortality score is also very high. And that goes for the very low portion of the graph too, that dark purple, where we see predictions around under 70% for the maternal mortality score. That's when under 5 mortality and sanitation are very low, right? And this also breaks into thresholds. So when we see, it looks like there's a threshold here where when we get over around 45 or 50% for our sanitation score, our model starts to predict a little bit higher value for maternal mortality. And same with under 5 mortality. And when we get to just above 60%, our model starts to predict higher for maternal mortality. So now that we saw how one variable influences the model's prediction, how about two variables? So here, similar to how we saw age and fare and how they influence the model's prediction of survival or not, we're going to look at under 5 mortality and sanitation and see how those influence the model's prediction of maternal mortality scores. So we can see in the top left or the top right here, we have this bright yellow, and that's the prediction of a high maternal mortality score. And remember, right, these scores, higher as being a good thing because it's a normalized score. It doesn't mean necessarily higher maternal mortality ratios. It means that country is actually doing well regarding maternal mortality. And that is when we see scores for sanitation and under 5 mortality very high in this top right corner. Similarly, we see in the bottom left corner, very So now that we saw how one variable influences the model's prediction, how about two variables? So similar to the way that we saw age and fare and their influence in the model's prediction of whether passengers survived on the Titanic or not, we're going to look at our important variables of under 5 mortality and sanitation and see how they influence the model's prediction of maternal mortality scores. So the first thing maybe to look at is the top right of the graph is that high yellow, which means a high predicted maternal mortality score. And that intuitively is when the sanitation score is high, as well as the under 5 mortality score. So that makes a lot of sense, right? We think when those scores are very high, our model's prediction of maternal mortality will be very high as well. And the same goes for the bottom left of the graph, where we see the dark purple, or the predictions of under 70% for the maternal mortality score, is when sanitation and under 5 mortality are low. And each of these line breaks is a threshold, right? As when these increase, this is the model's prediction of maternal mortality. And it tends to be, right, as both of these increase together, our model's prediction increases as well. So this is a good end to our random forest segment. And just to recap it, you might be thinking, okay, I'm still wondering a little bit why we're using machine learning. And it's really good at predicting things and realizing feature importance and important variables in relationships that are nonlinear. So things that might not be very clear in common statistics or correlation coefficients. It sees patterns that other statistics simply can't. So when we're asking a model to make a prediction and then asking about the most important features in making that prediction, we're doing something a little bit outside of statistics. And we're asking a model to make predictions, and we're getting back these nonlinear relationships or patterns that aren't so clear in more raw data analysis. And we're deriving that from a machine learning model. So it's almost one step further or thinking a little bit deeper about the interconnections in the data. And it should always be accompanied by traditional statistics and normal just data distributions and visualizations. But it's something a little special and something that has been driving lots of popularity and lots of things we see in the news and in studies are more and more using machine learning to look at relationships, right? That might not be so clear in some of the other lessons that we did if you applied that code or that way of thinking to the data. So now let's look at the challenges. We're going to edit our clustering code to change the number of clusters. And then we're just going to simply change our variable that we're predicting in the random forest model from maternal mortality just to whatever you choose. So we'll cover that a little bit more in the RStudio section coming up right now. So when we go to RStudio, we start here in our SDG analytics in R, and we can navigate to the R markdowns folder, and we should have our machine learning.rmd. And here we have the topics and the text that we see in the website. And here are the packages we use. I think this is the most of any lesson just because we're doing a few different things. We're using tidyverse here and janitor just like we did. We're using non-ER for the missing data visualizations that we used. We're using the cluster package for clustering, the random forest package for prediction that we just saw, Miss Ranger for predicting the missing values, so imputing those values with the random forest method, Facto Extra for making those cluster visualizations, and PDP for partial dependence plots. So when we start here, we see that we use read CSV in here, similar to the other scripts. We clean our names with the janitor package and the clean names functions for column names. And then we select only where normalized score exists in the column. So let's start by clearing my environment and starting fresh. Let's load these libraries. Read in our SDR data. Clean our column names. And here's where we select just where the column has normalized score in it. So we see lots of columns in our SDR data. There's ranks, missing values, spillovers, regional scores, populations, trends, dashes. So we only want columns where we see normalized score. So that's overall goal scores here, goal 12, goal 13. We're looking for just normalized scores. So this would be the first one we'll see in our data set with the filtering that we're doing. This normalized score for SDG1. And you'll see as we keep scrolling these normalized scores. So these are the columns that we're going to keep in this new data frame along with country. We'll keep the country column as well. So let's run that code. And here is SDR data, normalized scores. And so there are 99 variables, 98 normalized scores, and 1 country column. And that's what this looks like. Here we talk about missing data until we get to just doing the multiplication of how many cells there are. So 206 by 666 gets us 23,000 cells. How many of those are NA? We can use the sum is.na function on our data frame to get how many of those cells are NA. And that's just under 4,000. So again, around 19% of our data. And then when we want to look at, do some columns or variables have more missing data than others, or are NAs distributed equally across columns and variables? And to do this, we'll use the ggmissvar function from the non-ER package to display the percentage of NA values for each variable So we use the ggmissvar function here. We input our SDR data, normalized scores. We set the show percentage argument to true. And then we just play with the theme of our figure slightly to make it fit. When we run this line of code, we get this. And this is really small in our output. This was just to get it to fit nicely on the website. Maybe if we zoom in, it might be slightly more readable. But if you want to reference this, we'll just do it on the website because it is the same figure. But that is what that code produced. And then we asked the question, do some countries have more missing data than others? And for this one, we use the pivot longer function that we've seen. So we're creating a new data frame called SDR data normalized scores longer. We're making it from the SDR data normalized scores data frame, this one here. And we're using the pivot longer function, excuse me, and we'll pivot longer every column other than country. So pivoting longer, again, just makes the data frame longer. So we have less columns, but more rows. And it might make more sense just when we run this code, what that looks like. So now in our environment, we have SDR data, normalized scores longer. And now we just have 3 columns, the country, the name of the normalized score, and the value. So for Finland, under this normalized score, there's a value of 99.7. So we have this 3 columns. And with that, we can calculate the missing data by country using the missvar summary after we group by country, and we can ascend that data or arrange it in descending order. So when we do that, this is what that looks like. We have number of missing and percent missing, and that's where we see 100%, right, of some of this data is missing. So again, we went from our longer data frame, we grouped by countries, we used the missvar summary function to calculate the percentage of missing data for each country, and then we arranged the data in descending order based on that percentage missing. When we look at the data frame, missing data by country, this is what it looks like. So we have Andorra, a number of missing variables, and percentage missing. And we see here 27 countries have NA values for every single normalized score. What are they? We took a look on the course website, but here they are again, right? And so now we wanted to look and filter. If we make a list, right, of what those NA countries are, they're completely NA countries, is the name we give it. And we look at the missing data by country data frame, specifically country, and where that percent missing is equal to 100. And that's how we get these completely NA countries, this list we have here. And unfortunately, we cannot keep these countries in our analysis due to them not having any data for the SDG scores. So what we do is filter for only countries that aren't in that completely NA countries list. So that's that not in. So in percent in is, are they in this list of completely NA countries? We're using the filter function to filter out any country that is in there. So we only want the countries that are not in this list above. So when we run this code, you'll see we go from 206 observations to 179. Yeah, so we got rid of 27 countries that had completely NA values. And here, we use the ggmissvar function, again, just to make a new plot after we've dropped those countries. And again, you can reference that on the website because it's a little small here to view in RStudio. And this is the code we use to select only the variables where their NA is less than 20%. So we drew the line here, if you remember. We're going to select only the variables where their NA values are less than 20%. Now that we dropped those variables that had lots of missing data and the countries that had completely missing data, we can impute with that misranger function. So there's some documentation here on discussing random forest imputation if you're more interested in it. But we're going to impute that data or guess that data and name it SDR data imputed. So this data frame will have no missing data, and it will be generated from the SDR data normalized scores less than a data frame that we made once we dropped these columns that had more than 20% of the data missing. So when we run that, it takes a little bit because it's making predictions of all of these missing variables, and it's using a random forest method again. So there's multiple iterations and hundreds of decision trees happening as we run this code. It's pretty neat. And at the end of this, again, we'll have a data frame that has 0 NA values. Perfect. So SDR data imputed is this data frame that has no NA values in it because we imputed those values with a random forest method. And now we can get to clustering. So we use remove row names and column to row names to make the countries just the row names for each column. This is probably easier to see than it is said. So now for SDR data imputed, these countries are just the row names. And this is simply just the format that the data has to be in to go into the clustering functions. And now that our data is in that format, we could use that fviz nbclust to see again the number of clusters that are in our data frame. This is a suggestion, right? So what are the optimal number of clusters to feed into the next line of code, that k-means function? So we can go down here and we'll use k-means on our data frame, saying that there are 2 clusters that we'd like to separate the data into. So what countries are more similar to each other? There's 2 groups. And when we run that, we get this list here. And we can visualize those clusters, what countries fall into which one, which cluster with fviz cluster here. And that's what generates this plot. Again, this plot was hard to read. We saw that a little bit on the website. So we make this country clusters data frame, just looking at the clusters from the algorithm. So that's country clusters. And this is what that looks like. Just the row names and what cluster each country belongs to. So you can see these countries are in cluster 1. And as we keep scrolling down, we'll get to cluster 2. So we see Finland, Sweden, Denmark, Germany, all falling in cluster 2, right? Ireland, all these European countries falling into cluster 2. As opposed to cluster 1, we see not so many European countries, right? We see some countries in Africa. We see Venezuela, we see Honduras, we see Iraq and India. So yeah, we can make a lot of different hypotheses on why each country fell into each cluster. But again, this was grouping the data or grouping the countries based on all of the data or all of the normalized scores in our data frame. And it's up to us now too, if we'd like to keep this number of clusters. So let's look. And if we wanted to change this, right? Could maybe change this to 3 clusters. So we're not exactly following what this suggested we do, but it is still definitely interesting to see. And now the data will separate into 3 clusters. If we run this code again and we look at country clusters, there will be 3 options. So some countries falling into 2, some falling into 1, and some into 3. So now this is putting each country into one of 3 clusters, so a little more specific on the information. So I want you to play with this and see which countries fall into which cluster. And there's tons of analysis that can be done just with this data frame alone, right? And we can compare and contrast and see, is it very region oriented or a lot of countries in the same region falling in the same cluster? or is it not so geographically influenced, right? Are countries from all over the world falling into the same cluster? So that's questions that we can ask and you can ask in your homework and your final project. But let's move on to our random forest regression, right? So this is where we're predicting maternal mortality. So I wanted to show you what this looks like. So we're using the random forest function. We're naming it RF matmort, so standing just for random forest maternal mortality. And we only need to feed the random forest function a few things. So the first is the data frame that the second is the data frame we're going to use. The first is the variable we are trying to predict. So normalized score SDG3 for maternal mortality. This is the variable we're trying to predict with this data, the SDR data imputed. And we're setting importance to true because we want to know what the most important features or other variables were in making that prediction. So when we run this code, it runs relatively fast. And when we run just the name of the model, we can see its accuracy with mean of squared residuals, which I touched on, and percent variance explained. Then we could look at the importance. So what were the most important features in making this prediction of maternal mortality? And we can plot those. So here's our importance top 10 DF with filtering for just the top 10 important variables. When we plot them, it looks like this. So this is how we generate the sanitation, under 5 mortality, electricity access, and identifying those as the most important variables and making the prediction of maternal mortality. And then lastly, our partial dependence plots. So we use the partial dependence PDP package and the partial function to look at our random forest maternal mortality, and we give it the variable that we want to see how it influenced prediction. So in this case, our most important variable, our sanitation SDG score. And here we go, that's how we generated that plot where we see the predicted score as y hat for maternal mortality and how the normalized score for sanitation is related to that prediction. So when our sanitation score gets right above 40, we see a jump in our prediction for maternal mortality score. So we chatted about that. And again, we use that partial function, just feeding it our random forest and the variable we want to see on this x-axis, sanitation. And then lastly, we do a very similar step with looking at the partial function, but we're feeding it 2 scores now. So we want to see on an x and y axis how the normalized score for sanitation and the normalized score for under 5 mortality influence the model's prediction of maternal mortality. And this will take just a second, and we'll let this run, and we went over just the output of that model and some things and how we can interpret it in the beginning of this video. But again, yeah, we're feeding it our random forest, and then the 2 variables we want on the x and y axis here. And we get this plot. So now I wanted to talk about the challenge. So we already did this briefly, so it should be relatively simple to check out. And if you change the number of clusters to be different than 2, see what the new visualization looks like, and save the data frame and see what countries fall into what cluster and try to make some hypotheses on why. And then for challenge 2, we would like you to change the variable that you're predicting. So in the code chunk, scroll up here just to see it again. This is where we looked at and we inputted what variable we would like to predict with our random forest. So just changing this to another normalized score will completely changing everything, right? Because you're making a different prediction. So it'll be a different model. You can give it a new name. Then you could feed that name to see the model's accuracy and the variance explained. And you can keep this and just input your new model for importance and check out what are the most top 10 important variables in predicting the variable that you're interested in, the one that you input, and it will be different than these. And then check out, feed the most important features from here into this function, into our partial dependence plot, to see how the important variables influence the prediction of the variable that you choose. And then choose another one and see maybe the top two, right? The first and second most important variables in making the prediction. Feed them into this function and see what this plot looks like. It'll be different than this. So we just want you to run through that and tweak some of the code just to see that you're understanding the general idea of it and how to just change out certain variables and make different predictions and look at different numbers of clusters. So please, I know this is maybe the most technical part of the course, so come to office hours, ask questions, check it out, and we'll all walk through this together. And I think it'll be a really cool part for your final project to use some of this machine learning that we learned today. Thanks.